Previously, we have discussed a few different types of motion, constant velocity motion, constant acceleration motion. Today, we're going to talk about a special type, a special case of constant acceleration motion, which is free fall motion. So with free fall motion, as I said, it's constant acceleration, right? You have some object, you have mg going down, right? Force due to gravity, pulling it down, nothing pulling it up, right? We're also going to assume that this object is dropped from rest. So from rest, that's an important assumption as that will affect the results that we get today. So keep in mind, everything that we do in this video is free fall motion, a special case of constant acceleration, and we are doing free fall motion from rest only, right? Dropping it from rest. And so, as I said, it's constant acceleration, right? So we can do our constant acceleration equations. Y final equals y initial plus v initial y times t plus 1/2 ay t squared. But we've already made a mistake because we have not yet drawn our coordinate system. So that's positive y, and downward is going to be negative y. Okay. Well, as we said, we're dropping it from rest. The initial y is equal to 0. So this whole term cancels out. Okay. Now, we'll come back to this equation in a second here. But first, let's look at our force diagram again. Force diagram says that the sum of the forces in the y direction is equal to m times the acceleration component in the y direction, right? MAY. Well, what is that sum of the forces in the y direction? That sum is negative mg, right? And don't make the mistake of calling it just mg, right? This is negative. It's in the negative y direction. So negative mg is equal to may. M's cancel. Ay is equal to negative g. Now, this is an important point to hit for a second here. G is positive 9.8 meters per second squared. Okay? So the acceleration from free fall motion is not, I want to say this clearly, the negative comes from the fact that we are looking in the negative direction, right? And so we'll switch this around in a second where we do this as positive y, this is negative y, and then you'll see that that negative is not there, but the problem still works out. So I just want to point out that g does not equal negative 9.8 meters per second squared, right? G is equal to positive 9.8 meters per second squared. It's just a constant, right? G is a constant. The negative sign comes from the problem. It comes from the direction of motion. It comes from the coordinate system that you set up as this is positive, this is negative. Okay, so with that done, let's go back to the problem. So y final minus y initial is equal to 1/2, negative 1/2 gt squared, right? Plug in the negative g for ay. Well, that's delta y, and then it's just y final minus y initial. And let's take the 2 to the numerator, the g to the denominator, take the square root, and that's t. Okay, now let's, negative g in the denominator, and that's t. Okay, now this is two expressions. Let me write them a little bit more clearly. So delta y is equal to negative 1/2 gt squared. And then on the other hand, t is equal to the square root of negative 2 delta y over g. Okay, so we have two expressions for free fall motion that are both very important, right? Now let's look at this for a second. Delta y is equal to y final minus y initial. The ball falls downward. Y final is more negative, is less than y initial, right? So this part is less than this part, which means that the whole quantity, delta y, is going to be less than 0, right? Delta y is itself a negative quantity. So if you're concerned about the negative under the square root sign, which you should be at first, then you need to look closely at the problem and realize that delta y is always going to be negative for the way that we've set up our coordinate system. So t will be a positive quantity. We'll get a positive time, which is good. Same thing up top. We're going to get a negative quantity over here, but then that negative is going to cancel with that one, and so things work out. Okay? And so that is method number 1. Let's look at method number 2. Method number 2 says that this is negative y upward, and this is positive y downward. Right? We still got the same problem, mg pointing downward, right? But now mg is in the positive y direction. And so now our sum of the forces in the y direction is equal to MAY, as always. But now we have positive mg is equal to MAY. M's cancel. AY is equal to G. Okay? Now let's talk about the equation for motion. Y final is equal to Y initial plus V initial Y times T plus 1/2 AY T squared. Make that smaller, pull it over. T squared. Okay? Well, as before, V initial Y is going to cancel that whole second term. It's going to be 0. And then we've just determined that AY is G, so Y final minus Y initial is delta Y on the left side of the equal sign is equal to 1/2 G T squared. And now delta Y is going to be a bigger quantity, right? As the ball falls, it's getting more and more positive, right? And so a more positive number, delta Y equals Y final minus Y initial. I'm a little careless with my subscript F. So Y final minus Y initial, is some bigger quantity, right? As it falls, it gets to it gets more and more positive. So a bigger quantity minus the smaller quantity, it's going to be positive. So delta Y is greater than 0 here. And so once again, this equation works out great, right? This equation works out perfect, and it's completely equivalent to this version, right? It just depends on how you're measuring delta Y, and that's why we get different answers. Now, let's go on to solving for t. So t then is equal to 2 delta y over g, take the square root. And so you have this answer for t, where we don't have to worry about the negative sign in the denominator anymore. That went away, right? That never even showed up in the first place. This right here, positive g, right? And so we never had that negative sign in the first place. Delta y, as we talked about, is a positive quantity, so you're going to get a positive value for t. And so once again, I'll just rewrite both of these right together here. Delta y is equal to 1/2 g t squared, and t is equal to square root of 2 delta y over g. Okay, and that would be the two most important quantities that you can solve for. Take your pick depending on what problem you're trying to solve, right? But that's the idea of free fall motion. And so each second, to talk a little bit more theoretically about what's going on, each second that the ball falls, the acceleration in the y direction is g. It's a constant g, a constant 9.8 meters per second squared. So each second the ball falls, its velocity increases by that 9.8 meters per second, right? It has an acceleration of 9.8 meters per second, right? 9.8 meters per second squared. So that's what that's coming from. And I just think it's an important thing to try and wrap your mind around, say it a few times, get used to the wording of meters per second, right? Get used to that idea. And so with free fall motion, we can, in fact, add in air resistance. Now, I briefly mentioned before that there is quadratic air resistance and there's linear air resistance. But for the purposes of this video and for the purposes of just the course that we're on, I'm not going to bring up the air resistance at this time. However, you can read more about that in the website. One other thing to note is that you could do free fall on other planets as well. So other planets, right? And so I know moon is not a planet, right? But let's just talk about the moon, for example, as just another celestial object, because I have that value handy right now. So on the moon, the acceleration due to gravity on the moon is equal to 1.62 meters per second squared. But the really neat thing is the equations that we've derived still apply, right? These are still good equations. You just plug in g moon instead, right? And you could get an answer for the free fall time on the moon, right? Or for the free fall distance on the moon, right? Within a certain amount of time. And so it's a really powerful concept that we've just derived, because this free fall is not exclusive to our planet alone. And so for this video, that pretty much wraps up everything that we want to talk about. This is free fall motion, and there's definitely more that we could do to go even more in depth on this, but for now, this is sufficient.